Hi, welcome back. This video is going to cover engine types and constructions. It goes hand in hand with your Aviation Maintenance Technology Power Plant Volume 1 Handbook, so make sure that you read that in addition to watching this video. First of all aircraft engines are heat engines. They take energy and convert it from one source to another. So we start out with chemical energy, and really that's almost a shortcut because the chemical energy, the fuel, starts out as plants which grow as the result of the sun shining on them. Plants are really the oldest form of solar energy storage. Those plants in ancient times got buried and compressed and turned into oil. We refine that oil, turn it into fuel, and then we put it into the engine, mix it with some air that has oxygen in it, and we burn it in order to convert that chemical energy into heat energy. From there, the engine, then its job is to convert that heat energy into mechanical energy so that we can turn a propeller or turn a rotor blade and go through the air. General requirements are that it needs to be powerful. That's first and foremost. Typically for pilots, the more power, the better. Although it also has to be light. The Wright brothers, in part, got their Wright Flyer off the ground because they were able to make an engine that was light enough for the power that it produced, and they had to do that themselves. By the way, nobody was making an engine light enough in those days, so they actually had to go to their local machine shop and have a custom engine made. It has to be compact and streamlined if we want to go any sort of speed at all. And it needs to be economical in terms of the fuel that it consumes and how much it costs to maintain. It also has to be reliable. For obvious reasons, we don't want our engines failing all the time. So when we go to select an engine, we ask ourselves a set of questions. And the first one is, how much power do we really need in order for this aircraft to be viable? How fast do we want to go? What does the flight profile look like? And by that I mean how high do we go? But also how short are the flights? You might select a different engine if each of your flights is going to be 2 or 3 hours versus one where we do like our 152s and R22s. A lot of times we start them up and just go do 1 hour of flying at a time, or sometimes even less. Who's going to be flying it? It would be pretty foolish to put a $250,000 turboshaft engine into the hands of a student pilot because it could be so easy to burn that engine up. So it has to be simple to operate. What are the economic realities? Again, not very efficient to learn to fly in an aircraft that costs $500 or $1,500 an hour to run. What are the political or marketing considerations? For instance, the Cessna Skycatcher originally came out with a Rotax engine on it, but the flight schools didn't like it because they weren't used to that kind of engine. It was actually a better airplane in my opinion when it had that Rotax on there. Instead, they went with the plain old Continental O200, the same engine, almost virtually unchanged from my 1969 Cessna 150. So those types of considerations also come into play. Types of engines, we categorize piston aircraft engines in general by how the pistons are arranged on the engine. The most common one being opposed, and by that we mean that the cylinders on the engine are sticking out sideways opposite from one another, and I'll show you a couple of pictures here in a second. The number 2 kind is the radial, and once again in this case the pistons are sticking out in a circle radial to the center of the engine. Inline is obviously a row of pistons in one line. V is two rows of pistons in a V shape. And then when we move to turbine engines, we have three basic configurations: straight turbojet, turboprop, and turbofan, and we'll talk more about those later in the term. We also have diesels that are being certified and now flying, including in the Diamond D42s that are operating out at Hillsboro. If you've heard those things flying over, you'll notice that they have a very different sound to them. They're maybe a third as noisy as the old Seminoles, and they have some real advantages to them as well. So here's a picture of the one that very similar to the one that you're probably flying right now. This is a horizontally opposed Lycoming engine, four-cylinder, much like we have in the 152, the 172, and the R22. All use an engine that's very, very similar to this. As you can see, if you look inside, the finned parts here are the cylinders, and they are arranged, there's four of them, they are arranged opposite one another on each side of the engine and pointed directly away from them. So we call this an opposed engine. Here's a side view of it, kind of all by itself. And we can see the cylinders once again sticking out sideways opposed to one another. This big thing hanging off the bottom is the oil pan. This oil dipstick sticks down into the pool of oil inside that oil pan. That's what you're testing when you check the oil. And everything is mounted on this case in the middle. The propeller is mounted on the crankshaft that sticks right straight out the front of the engine. If this were a helicopter, the engine would be pointed in towards the transmission to convert that to lower RPM for the main rotor. Here's a six-cylinder version of pretty much the same engine. They just added two more cylinders onto the back, had to redesign the case, obviously. They go all the way up to eight-cylinder horizontally opposed engines. This is the Lycoming IO-720. The IO means it's injected. The I is for injected. The O is for opposed. And 720 is the number of cubic inches of displacement that it has. Here's an example of a radial engine, the Wright Cyclone R1820. So the R stands for radial in this case, 1,820 cubic inches, believe it or not, all in these nine big gigantic cylinders. The nice thing about radial engines is that you can stack more banks of cylinders in behind it. Here's an engine, the R4360, which is essentially a 7-cylinder radial engine, but four of them stacked one behind the other. So four banks of 7, 28 cylinders, 4,360 cubic inches. Imagine having to change the spark plugs on that one. And yes, there's two on each cylinder, so that makes 56 spark plugs that you'd have to clean on this one. Here's that engine mounted up in an actual Reno Air Racing engine. And you can see it's a mess in there. That's a lot of power, though. That's 3,000 horsepower even stock, and of course down at the Reno Air Races they managed to get even more out of them there. Here's an Allison V12, and so here we have the banks of cylinders. You can see one on this side, and there's another one at about the same angle on the other side. And there's 6 cylinders on each side, and they're arranged in a V shape. And that's where we get the V from in V1710. So by now you've seen that the basic nomenclature has some commonalities here. We have a letter up front that designates the arrangement of cylinders, so O for opposed. This, by the way, is your Cessna 152 engine. Or at least on some years, it's this engine. So O is for opposed. This is the specific model number. The numbers and letters don't really mean anything. They're just a code. There's a book of codes in content in D2L if you want to look up exactly what N2C means. And this is the displacement in cubic inches of that engine. All of that is found in your pilot operating handbook, also known as the Pilot Information Manual. And one of the first things you ought to do in this class is look up everything that you can find in your POH about the engine on your aircraft. So let's talk just a little bit about how these engines are put together, and we'll go into much more detail as we go on this term. But this is just going to be a brief overview of the big pieces. So we'll start with the cylinder. The cylinder is a chamber in which the fuel is burned, and it actually comes in two pieces, the cylinder itself and the head. The cylinder is made of steel, the head is made of aluminum. This causes some challenges. It's very easy to start cracking that aluminum head if you're not careful. But they work pretty well this way. The two are screwed together at the factory. They chill the cylinder and they heat up the head, and then it's an interference fit. So then when they get to the same temperature, there's no way you're going to unscrew this thing. Very, very rare for those to ever get unscrewed once they've been assembled at the factory. So that's the cylinder. We'll talk more about the insides of those cylinders as we go along this term. And then we also have a couple of valves, and the valves let the new fuel-air mixture in and get the old exhaust out as the engine runs. And so there's an intake valve and an exhaust valve. There is a camshaft, some lifters, push rods, rocker arms. All of those work the valves and open and shut the valves at just the right time. Here's some cross sections of valves, and what you'll find as you read through the book is there's a lot of variety here. Some of them are sodium filled, which allows better heat distribution. One of the big challenges with valves is they're sticking out there in those flames inside the combustion chamber, and so we have to have a way of conducting that heat away and out of the valve, and sodium helps us do that. And there's various shapes, and those shapes give us various characteristics for heat distribution and vibration and sealing and so forth. Here you're looking straight down on what we call the top of the cylinder, which is where the valves are. And the top one here is the intake valve. The bottom one is the exhaust valve. You can tell that, by the way, because you can see down here there's some extra cooling fins, and those are usually around the exhaust valve. We've got two valves. One, again, the exhaust valve here has the rocker arm installed on it, and the rocker arm is what opens and shuts the valve. So you can see some really big springs. Those hold the valve shut. And when the engine turns, it turns a camshaft. The camshaft has lobes on it that lift these push rods that you see poking out here of these smaller holes. And that rocks the rocker arm like a teeter-totter and presses down and opens the valve down inside the combustion chamber. Here's sort of a side view cutaway of how all that works. Once again, we have the cam down below, and in this case we have a cam ring, and the cam ring is something you find typically on radial engines. A cam shaft works just the same way. We'll look at some examples in class. But you'll see this lobe here comes around, and when it goes underneath the cam roller, it pushes up on the tappet, also known as the lifter. And then the lifter pushes on the push rod, and the push rod rocks the rocker arm. The rocker arm pushes down on the valve and presses the valve down against the spring and opens the valve inside. And so if it's an intake valve, it's letting a new charge of fuel-air mixture into the cylinder. If it's an exhaust valve, it's opening up to let the exhaust back out again. It's all geared together so that they open and shut exactly exactly the time that they're supposed to each revolution. Here's a cutaway looking from the front of the engine at the valve operating engine. And I just said everything's geared together so that the valves open and shut just where they should in each revolution. Actually, the valves only need to open every other revolution because it's a four-stroke cycle. The four strokes are intake, compression, power, and exhaust. So that means the intake stroke, the piston's coming down. The compression stroke, the piston's going up and compressing the fuel air mixture. At that point, both valves are closed so that we can compress the fuel air mixture. Then we light it with the spark plug, and then that pushes the piston back down again, and the valves are still closed. And then we get the exhaust stroke where the piston goes back up again and pushes the exhaust out through the open exhaust valve. And then we get another intake stroke, and during the intake stroke, the intake valve is open. And so it goes, except really, really, really fast. We'll talk more about that when we get to engine theory. Here's a close-up of the cam lobe on the actual lifter body, showing how a camshaft can push on that lifter and push the push rod for us. Here's a cross-section of that with the cam over on the right. Again, notice the little lobe on the cam, so when that turns around, it's going to push on our lifter, which then pushes on the push rod, which pushes on the rocker arm, which opens our valve. We also have pistons inside the cylinder, and they are what are going up and down, and the pistons have rings on them to seal them on the inside of the cylinder. And there's three distinct types of rings. There's the compression ring, which seals in the expanding gases so that we get the good out of them. There's the oil control ring, which spreads a thin film of oil on the inside of the cylinder. And then there's oil scraper rings, which they don't label here, that just dump excess oil back down into the crankcase. There's all sorts of different shapes that pistons come in. You don't have to worry too much about that. But it is interesting to look like. Notice there's a piston pin pictured here. That goes through this hole, and that is what is used to hold the connecting rod onto the piston. And that's the connecting rod right here. And you can see the pin going through there. This is a picture of a connecting rod. The small end is up inside the piston. The big end is what wraps around the crankshaft, and as the piston goes up and down in the cylinder, it's cranking on the crankshaft, just like you would crank a handle. Here's a picture of what happens when the connecting rod breaks. When the connecting rod breaks, it pops out through the side of the crankcase and makes a big hole in your engine, and all the oil runs out. And that makes the engine stop working. So you have now an engine failure, and it's really expensive to fix because you need a new engine. So that gets us this far. A lot of times we'll have dynamic dampers and things like that attached to the crankshaft. That helps take out vibrations out of the crankshaft. Here's a picture of the inside of an engine, and you can see both shafts. You can see the crankshaft on the left and the camshaft on the right, and notice they're geared together right down here at the end. So once again, the valves are opening and shutting at exactly the right time in the four-stroke cycle. And because the valves only have to open half of the revolution, so every other revolution, the gear on the crankshaft is smaller. The gear on the camshaft is bigger, exactly double the size, so the crankshaft has to turn twice for every one time the camshaft turns. The crankcase holds everything else together, and so it has to be very carefully designed to handle all the stresses of the engine. Here's a cutaway of the cylinder assembly. The cylinder assembly is everything to do with the cylinder. So the cylinder itself, the head, the valves, and the piston. If you order up a cylinder assembly, all that stuff comes with it. I can tell you from experience that a Cessna 150 cylinder assembly for the Continental O200 is going to run you about $2,000. So here's the whole engine all kind of exploded apart. We have the crankcase here that everything else is going to be pinched inside. Notice that it splits in two, and both the crankshaft and camshaft are just pinched between the two halves in the bearings for each one of them, and they're just plain bearings. And then they're once again geared together at the end so that the camshaft turns at half the speed of the crankshaft. And then the cylinders are bolted onto the crankcase. And then there is an induction system, this spidery looking thing that bolts on to the bottom of all the cylinders. In this case there's 6 cylinders, so there's 6 tubes coming up. The purpose of the induction system is to split the fuel air mixture from where it comes out of the carburetor into 6 separate streams. And that means there are many of these pipes into one, and we call that a manifold. That is the intake manifold, this beast right here. And so when you get to an aircraft that has a manifold pressure gauge, we're talking about the pressure inside that intake manifold. Then we have an oil sump and various other accessories that get bolted onto the back of the engine at the accessory case, which has all these mounting pads on it. And those can all be driven by those same gears that are at the aft end of the camshaft and crankshaft. That's it for this presentation. Make sure that you do the reading along with this, and we will see you for the next video.